Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our Bellwork today, where we're making a connection between a differential equation and the slope field that it produces. We can make a slope field based on the differential equation by choosing some x and y values, some ordered pairs x comma y, plugging them into my differential equation rule and evaluate, just like we would evaluate a function rule back in middle school. Just that now we'll be producing a slope value. A slope value for my solution curve, should it come in the nearby vicinity, it must follow the same direction. So we're going to use that, right, to generate our eventual sketch of my particular solution. All right, so let's go ahead and get a slope field first. We can go ahead and choose some points, x comma y, and evaluate them into my dy dx formulas. So I could choose some x values, some y values, and then evaluate them in my dy dx. And so here we go. Let's go ahead and choose anytime x is 0, right? Anytime x is 0, what will be true about my slope value? Well, anytime x is 0, regardless of what constant my y value coordinate is, the result's always going to be 0 for our slope. So I can fill in, right? I can fill in all of the horizontal tangents whenever the x coordinate is 0. So when is the x coordinate 0? Well, all along the y-axis, right? So we could fill in all those, right, in one fell swoop. Oh, let's do a different color. Oh my! Did you see that? Oh wow! That's too bad. I think we'll be able to recover that lost soul though. There you go. So let's go ahead and draw in our different color there. So we've got horizontal tangents, little mini tangent lines, at all the places where the x coordinate is 0. Similarly, if the y coordinate is ever 0, right? If the y coordinate is ever 0, then for any constant k that the x coordinate takes on, still the overall value of the slope will be 0. So we've got some more mini tangent lines that we can draw in. We know whenever the y coordinate is 0, that's down here. Oh boy. We're gonna have little horizontal tangents. Awesome. Everybody good? So we can take care of all those specials all at once. Now let's get a sense of what the slope field is doing, right, in each of our 4 quadrants. And so I can go ahead and choose some more order pairs, like 1, comma 1, negative 1, comma 1. And let's see what happens with these. So when x is 1 and y is 1, my slope is 1. So we can fill that in. Oh, let's do that again. I want to be able to see this a little bit better. Cool. When x is negative 1 and y is 1, overall value negative 1. There, fix that problem. What about 1 comma 2? Well, 1 comma 2 results in a slope value of 2. So we're a little bit steeper here. Negative 1 comma 2 is negative 2. And we start to get a sense of, well, what this might look like. So now negative 2 comma 1, negative 2 comma 1 is going to be overall negative 2. And negative 2 comma 2, negative 4, and so on and so forth. And so we're getting an idea here of what my slope field is looking like. And we're showing that with many tangent lines. We can do the same thing for my negative y values. For example, 1 comma negative 1 is going to be a negative 1 slope. 2 comma negative 1, negative 2, so a little bit steeper, a little bit steeper, a little bit steeper still, and so on and so forth. What about negative 1, negative 1? Well, that's going to be overall positive 1. Negative 1, negative 2, overall positive 2. Negative 2, negative 1, overall positive 2. Negative 2, negative 2, positive 4, and so on and so forth. Go ahead and raise your hand if you had the same graphical representation of the slope field. Yes, the slope field. Okay, good. So we can evaluate my dy dx rule, my slope, at different points x comma y, and then sketch in mini tangent lines. So that's how we do a graph. Now let's go ahead and estimate the solution curve that contains the point 1 comma 2 by sketching a graph. And so this is where we think of that slope field, right, as a map, a current of the river. And if I take my initial value and think of it as a leaf, I drop that in my slope field, and I'm going to follow those directions, those little signposts of the mini tangent line, and see where that curve would extend in either direction. You could also think of that as dropping the die, and you're in the current and watching to see where that die is taken, right? Where the colors go based on the current. Okay, so let's go ahead and do that. 1, 2 would be right about here. Right, 1, 2. And if we were to estimate that particular solution curve that contained that point, we want to be following the direction of these many tangent lines. And so it looks to me like if I were to sketch this in, perhaps I'd get, I need to be parallel to the nearest one every time. So I'm going to guess something maybe like this. Something maybe like this. Now, that's just an estimate, right? That's just an estimate. Let's see, did I get the whole thing? There. So that's just an estimate of the solution curve. I'm not sure right now, right? I'm not sure right now where that y-intercept is on my solution curve, but I bet we have a way to figure that out, right? We do, because we have the differential equation and initial condition. So we could pin that down, right? This red solution curve, we could pin that down algebraically and exactly. So let's see then what number 3 has to do. Find the particular solution curve that contains that point algebraically. So first thing, we need to separate the variables to multiplication or division. Is this differential equation separable, right? Is this separable? Riley, F cursive?
Yeah.
Yeah, absolutely. We can divide over the y and multiply over the dx. And so for my first step, we'll go ahead and separate the variables. After we've successfully separated the variables, got the dependent on one side, the independent on the other side, we'll go ahead and integrate both sides. Now we do have an opportunity to use natural log. When I have that quantity on the bottom of the first power, that does authorize the use of natural log as an antiderivative, and so it's okay to integrate here for natural log absolute value of y. Again, we get a plus c, but we'll group that constant integration over on the independent variable side. Power rule yields x squared over 2 and then plus c. And we've seen how we could either plug in my initial condition right now and solve for c, rewrite and then solve for y at the end, or we could continue on, solve for y and find the general solution y equals, and then plug in for c and rewrite. It's about the same amount of work either way. I like to go and find the general solution because that constant c can absorb some of my inverse operations. And so I'm going to go ahead and solve for y first and plug in my initial condition last and then rewrite. All right, let's go ahead and do that. So I've got natural log of absolute value of y. How do I do natural log? Easy cheesy, e to the. And so we can go ahead and say absolute value of y is equal to e to the x squared over 2 plus c, all up in the exponent. We now can split out my sum or difference in the exponent using the properties of exponents and rewrite that as a product of quotients. I'm sorry, a product of powers with like bases. So we'll go ahead and keep this absolute value bars for one more step. We'll break this up as e to the c times e to the x squared over 2. And now we can get rid of those absolute value bars. Keep in mind the absolute value bars return the same as the quantity inside if the quantity inside is positive, but they return the opposite of the quantity inside if the quantity is negative. So I'm going to go ahead and get rid of the bars by applying positive and negative. And now we'll go ahead and group this plus or minus e to the c, which I don't know, right? Which I don't know, it's some constant. I'm going to call that a, right? I'm going to call that a for some constant we don't know that we're about to pin down. And I get y equals a times e to the x squared over 2. All right, how do I figure out what a is? Now we'll utilize that initial condition. Did I get more space anywhere? No, I didn't. So I'm going to utilize the initial condition when x is 1, y is 2, and rewrite. So we'll go ahead and say 2 equals a e to the 1 squared over 2. So e to the 1 squared is 1 over 2 is e to the 1/2. So it looks like a equals 2 over e to the 1/2. And recall that e to the 1/2, right? E to the 1/2 is the same as the square root of e. So depending upon how you'd like to write this, solving for a by division, I get 2 over e to the 1/2, which is the same as 2 over root e. Does that work? All right, let's go ahead and rewrite that. Whenever we did the substitution, which was right here, to pin down that constant, we need to rewrite that line to get our particular solution. So we still need to rewrite y equals a is 2 over root e to the x squared over 2. Awesome. All right, so let's go ahead and see if we can't make a picture of that, right? And on the window, negative 3 to 3 and negative 3 to 3. Okay, so this is exciting. We're going to go ahead and generate a slope field using our program from yesterday. So everybody, I can't install it on the emulator software because it's newer than my program code. Well, I'm just going to do it with the handheld, and we're all going to do it together. So please pay attention. We're not going to put the solution curve in first. Instead, we're going to run the slope field program first. And so everybody, go to your y equals menu. Go to your y equals menu. I can do that part on there. On your y equals menu, you're going to enter the differential equation, x times y. And to do that, you're going to do your alpha button for alpha y. You'll still use your variable button for the x one. So I'm just trying to pull this over so you can see what I'm entering. Okay, so on our y equals menu, we're going to enter our differential equation, which was dy dx equals x times y. So in our y equals menu, we're going to enter x times y. Where do I get y? Alpha y. What is that? 1. Hey! Great. So that looks weird because we got x's and y's mixed together. So my y1 is programmed to be the dy dx. That's programmed to be my y prime, my dy dx. Okay? So we've got that. Now we need to adjust our window. So what does it do? Negative 3 to negative 3. So manually adjust your window, please. Negative 3 to 3. So we've got negative 3 to 3. Yeah, you guys good? Okay, can't wait to do it. Ready? So now what we're going to do? We're going to do program. We're going to execute. So when you do program, you should have slope field. All right, you have slope field? You're going to press enter, enter. Are you executing? Yes. Yes? Did it work? Did it make a nice thing? That's pretty awesome. Mine is not. Okay. Awesome. So now what are you going to do? Now we're going to superimpose our particular solution curve on our slope field. Okay, and so for this, we're going to go ahead and do y equals, and now in y2, you're going to add the solution curve that we got. So this is now a regular y equals. This is a regular y equals, not a y prime equals. This is our solution curve. What's our solution curve? Well, we got 2 over root e, close radical, times e to the, my function, e to the x squared over 2. Right? So we've got that. That's in your y2. I'm going to change the line style so it's fatter. So I'm going to change the line style here. I want to change it to thick. Okay? Well, whatever. I changed mine on this one to like thick so that I can see it. It'll overwrite those little tangent line slopes. We don't want them the same size. We want to really see that new function. Okay, and now I'll go ahead and do the graph and see what you guys get. Did that go? You got it. There you go. Try. So now go ahead and graph. Okay, ladies and gentlemen, so let's go ahead and make sure that we have our OTL number 3, we want to staple our OTL sheet on there, right? That was the big page, OTL number 3. It had the figures on the back, so if you kindly staple that. And Sammy and Michael, if you guys can start with the staple over there, and Courtney and Kobe, if you guys can start with the staple over here. I'd appreciate that. Recording again. Okay, ladies and gentlemen. So what's going on today? Well, what we're going to do is continue making our connection between our differential equation, the slope field it produces, and the particular solution curve or our family of solution curves. And we're going to do that by this matching activity, which is really good because it allows us to tackle different differential equations and solution curves via different methods depending upon what it looks like. And so in some cases, you're going to be able to match the way you did considering special slopes, or by choosing ordered pairs x, y, like the Bellwork. In other cases, you're going to have to start the solution curve and differentiate it, and then solve for y prime to get your dy dx and match it that way algebraically. And in still third instances, you're going to start with the differential equation and integrate it, right, like a separable differential equation if possible, and see if you can't match it to the particular solution curve that way. And so this is a great activity because you've got different tools at your disposal, and you're going to go ahead and figure out, you're going to have to probably use each of those tools at least once in your matching activity. First, though, I want to go ahead and take a look back at number 9 from our 7-4 slope field activity. This was tricky. It was our first foray into matching. On your upcoming Unit 7 test, remember that's next Thursday the 25th, you'll have to match. You'll have to do some matching with slope fields and their differential equations. And so let's go ahead and see how can we make this easier, right? How can we make this easier without having to spend the time choosing, right, 7 or 8 points like we did for Bellwork and sketching the graph of each of those differential equations? Well, we can kind of consider our special slopes. And so what I mean by that is, are there certain x coordinates or y coordinates that would be responsible for either those horizontal tangents or vertical tangents, right? That'd be undefined slope for any of these equations, and these differential equations. And so let's go ahead and consider, B looks familiar, doesn't it? Right? X times y. Anytime we let an x coordinate, and letter B, the equation, be 0, I would expect to see slopes that are 0. Graphically, that would be what? Little horizontal tangent lines. And so I'm looking for little horizontal tangent lines whenever the x coordinate is 0, so along the y-axis. And I see that satisfies a couple of them. Slope field 1 has horizontal tangent with x equals 0. So does slope field 4, right? So have I got my answer based on that? No. But consider what happens when y equals 0. When y equals 0, then I also have horizontal tangents. So I would expect to see horizontal tangents on the x-axis whenever y equals 0. So which of these slope fields has horizontal tangents on the x-axis and on the y-axis? Riley? Yeah, number 4. Furthermore, when x and y are both positive, we've got positive slopes. When x and y are both negative, negative times negative is a positive slope. When one of the coordinates is negative, but the other is positive, we have negative slopes. And when one of the coordinates is positive, x positive, y coordinate negative, we've got negative slopes. And so does everybody see that? When we put it all together, it looks like B is going to have to be 4. Is that right? So number 4 matches B. Let's go ahead and see if we can kind of do a similar analysis. Let's take a look at C. And so as we look at C again, whenever the x coordinate is 0, it should result in a slope that is 0. So again, I'm looking on the y-axis to see if there's any horizontal tangents along the y-axis. And so we've already taken care of B. Horizontal tangent on the y-axis? No. Horizontal tangent on the y-axis? No. Horizontal tangent along the y-axis? Yes. What happens when y is 0, right? When y is 0, what does that do to your slope? Well, it makes a 0 on the bottom of a fraction. A 0 on the bottom of a fraction means undefined, right? What kind of slope is undefined? A vertical tangent. And so when y is 0, namely along the x-axis, I would expect to see a vertical tangent. So does that satisfy any of these? Yeah, it looks like this would have kind of vertical tangents. You guys see that? Vertical tangents there along the x-axis, horizontal tangents along the y-axis. And so by using kind of my special slopes, that is looking for horizontal tangents or vertical tangents, I've narrowed down letter C should be number 1. Is that right? Letter C should be number 1. All right. So what else can we do? Well, let's keep going with this. We saw the undefined thing was fairly helpful last time. So if y coordinates are 0, that's along the x-axis. I expect to see 0 slopes for the slope field produced by equation D. Let's see if there's any more 0 slopes along the x-axis. Yeah, so it looks like this one has 0 slopes along the x-axis. Do you guys see that? And if the x-coordinate were 0, if the x-coordinate were 0, that's along the y-axis. I'm expecting to see undefined slopes, vertical slopes. So it looks like D has to be slope field 3. Is that right? Slope field 3. So this looks like D and slope field 3. Okay, which means process of elimination yields A. But let's pretend we did A first. What kinds of strategies could help us with letter A? So let's see that it wasn't the last one. We didn't know exactly where it goes because there's only one of 4 missing. Let's pretend we were doing it at the beginning. So what things can we analyze? Well, we could consider for what coordinate pairs my overall slope is 0 again, right? And so when would I have 0 slopes? Well, I'd have 0 slopes when what's true about the value of x and y in my order pairs? They're the same. So I'm thinking of things like 2, 2, 3, 3, 7, 7, negative 2, negative 2, negative 5, negative 5. So it looks like along the diagonal, along the identity function, I would expect to see what kinds of slopes? I'd expect to see horizontal slopes. And as I look here, it looks like I've got this sort of negative slopes are turning into positive slopes right along the identity. So you guys kind of see that? So this, right, this graph looks like it has horizontal slopes when the x-coordinate is equal to the y-coordinate. That will result in an overall value of 0 for my slope, dy dx. I could also consider when my slopes would be positive versus negative. And so what values of x and y, what kind of order pairs would result in a value of dy dx that's positive? Well, in order for that to happen, right, the x-coordinate would have to be larger than the y-coordinate. A larger x-coordinate minus a smaller y-coordinate would result in a positive overall value of this difference. And so when is the x-coordinate graphically larger than the y-coordinate? So I'm looking farther to the right than I am up. So farther to the right than I am up, that means I'd have kind of this over here, right? Over here, I'm farther to the right than I am high. That's resulting in positive slopes. When would I have negative slopes? Well, I'd have negative slopes. When this difference were negative, that would mean the y-coordinate is larger than the x-coordinate. And so anytime my y value, I'm higher than I am to the right, it looks like, well, over here, right, my y-coordinate is larger than my x-coordinate. And so I'd expect to see no negative slopes, and that is the case. And so if we had started with letter A, we could still reason out the slope field 2 of the graphical representation. And so I'm getting Cadba, like Cadbury egg, so I'm getting Cadba. I can always get back to food somehow, right? I'm hungry all the time. Yeah, I just had breakfast. That's okay. Still hungry. So it looks like we've got CADB. All right. So can we use that to our advantage for the matching activity? Absolutely. So what kind of tips for success will we have with our matching? Again, we're trying not to use the slope field program at all. We're trying to do this, right, analytically, using our brains and also pencil and paper if we have to do some integration or some differentiation. And then if you're still stuck, then you can use the slope field program. But what I'm saying is don't go to the slope field program as your way out. This would be a non-calculated exercise on the exam. All right, so what do we mean by tips for success? Locate key slopes. So what coordinates, x comma y, result in 0 slopes? So what x comma y result in 0 slopes? I'm not sure which particular one I put on your note sheet, but I'm thinking here, key slopes, I'm thinking like horizontal tangents. Versus vertical tangents. When will the slopes be 0, right? When will the slopes be 0? When will the slopes be undefined? When will the slopes be positive? Right? When will the slopes be positive versus when will the slopes be negative. So these are all good things to think about. Bless you. Right? So what ordered pairs x comma y would result in zero slopes, undefined slopes, positive slopes versus negative slopes? Can be a good way to narrow down the options. How can one match the differential equations with the correct original equation? So now if we take a step back graphically, we've also got a couple of attacks that are pencil and paper algebraically. And so regardless of the graphical representation, recall that we could solve a separable differential equation and see what particular solution, or at least what solution family is produced. And so we could right, integrate the differential equation and keep in mind that we can only do that if it's separable. And there's several of these differential equations on your matching activity that are not separable, so you won't be able to use this as an option. But if it's separable, though, then we can separate and solve to find the general solution. Right? And that would involve integration. But I'm writing integration because then that's an inverse operation we know from the fundamental theorem of calculus for differentiation. What else could we do? We could differentiate the particular solution, right? Rearrange it, try to solve for y prime, and see if it, through substitution, ends up equaling the original. So our next option would be to, or another option rather, depending upon what it looks like, would be to differentiate our solution curve. That's not going to work for all of them. This technique of integrating the differential equation is not going to work for all of them, right? Sometimes it's going to be difficult to locate those key slopes, but together, by having all of these as resources and strategies at your disposal in your tool bag, then I think that together with your group, you're going to be able to reason out the correct matches. There's a single stamp issued today based on correctness, based on accuracy of your final matching on the worksheet. And so today we've got to be accurate in our final matching on your worksheet. And once you have it correct, right? Once you guys all agree, you're going to call me over. I'm going to check it out, right? And if we match and you have the correct matching, then you'll go ahead and get a stamp at the end. So this is a cool activity because we've got lots of different ways you can go about it. That's for printing for you. And we'll go ahead and get going on the matching worksheet. One at the end based on accuracy. I'm going to pause the recording if you guys scooch into your groups and get going right away. Hopefully we'll get a lot of stamps today, a lot of accurate stamps. I'm going to call in individual groups to share some of the strategies you use in order to match the differential equation with its graph of a slope field. And finally, a solution curve. So summarize the strategy you and your group use to match the original equation, differential equation, and slope field graphs. And I'm going to call on you, and we want to get at least three things up here. And so your group should be ready to share any of those three things. Bless you. So what's one strategy you use to help with your matching? Matching? Maggie?
It's looking for X's and Y's on the bottom of actions so that you can harass and
Absolutely. If you look for X's or Y's on the bottom of your differential equation, on the bottom of a fraction, that can help you identify undefined slopes where we had vertical tangents. And so we can call that as sort of locate key slopes. So we can think about locating the key slopes. And one key slope that Maggie mentioned was undefined slope, right? Undefined slope. Because they were vertical tangents, and so they're easier to see as you're looking at the slope field. All right, good, thanks. What's a different strategy? Riley, E?
If you look at the differential equation, it only equals either x or y.
Yep.
If you look at the graph, it only change with respect to that variable.
Absolutely, and so some of the differential equations were solely dependent on either x's or y's, and so that way you could look all the way across or all the way vertically and you have the same slope. So we kind of narrow down some differential equations? Depend only on one variable? So their slope fields then were consistent either all the way up in a row or all the way across in a row. Good. What's a different strategy? A different strategy. Sophia?
We looked at each quadrant individually, so like the x-values were negative and the y-values.
Absolutely. So that would help you determine the sign of the slope. And so consider sine of slope. Excellent, you guys. Have a wonderful day. I'm going to go ahead and add the differentiate a solution curve and integrate a differential equation. Have a great day.
Mitch Zabel, Stephanie Wallen, and Casey Scott, 2 items to pick up in the office. Thank you.